There is a dream that lives in the human imagination, a dream of sailing past distant suns, of watching strange new worlds rise on the horizon, of crossing the vast ocean of stars that we call the Milky Way. It is one of the most beautiful dreams our species has ever entertained. And yet, when you sit down with the actual physics, when you let the numbers speak without softening their message, that dream runs headlong into some of the most unforgiving walls that nature has ever constructed. Not walls built from a lack of engineering cleverness. Not walls that a more advanced civilization might one day dismantle with superior technology. Walls built from the bedrock of physical law itself, from the geometry of space-time, from the nature of energy and mass, and from the cold arithmetic of cosmic distance and cosmic time. Let us begin with the galaxy itself, because most people have no visceral sense of what the Milky Way actually is in physical terms. When you look up at a clear night sky and see that faint band of light arching overhead, you are looking at roughly 200 to 400 billion stars, all gravitationally bound into a disk that spans somewhere between 100,000 and 120,000 light years from edge to edge. Now, a light year is the distance light travels in one full year. Light, moving at approximately 300,000 kilometers per second, covers about 9.5 trillion kilometers in 12 months. And the galaxy is 100,000 of those units wide. That number has a way of dissolving ordinary intuition entirely. If you somehow compress the entire solar system, everything from the sun out to Neptune, down to the size of a single coin, the Milky Way on that same scale would still stretch for roughly 11 kilometers. The galaxy does not merely dwarf us. It operates on a register of size that human experience has no natural vocabulary for. Now, into this setting, we place the central character of our story, which is the speed of light. Einstein showed us, through the special theory of relativity, that the speed of light in a vacuum is not simply the fastest thing we have so far managed to achieve. It is the absolute maximum speed at which any information, any energy, any matter of any kind can travel through space. This is not a technological ceiling. It is written into the mathematical structure of space-time as a fundamental constant. And that limit sits at roughly 300,000 kilometers per second, which sounds extraordinarily fast when measured against anything we encounter in daily life. A commercial aircraft travels at roughly 1 kilometer per second. Even the fastest spacecraft humanity has ever launched, the Parker Solar Probe, reaches speeds of around 200 kilometers per second at its closest approach to the sun. Light still outruns that by a factor of 1,500. But here is where the numbers turn brutal. Even traveling at the speed of light, which no object with mass can actually do, crossing the Milky Way from one side to the other would take 100,000 years. The center of our own galaxy is 26,000 light years away. The nearest star system to our sun, Alpha Centauri, sits 4.2 light years distant, meaning light itself needs 4 years and 2 months to cover that gap. Now imagine trying to reach not just the nearest neighbor, but the far rim of the galaxy, where star systems exist that no human eye has ever resolved into individual points, where the light reaching your detector left its source before our species had even begun carving stone tools. 100,000 years at the speed of light, and we cannot travel at the speed of light. This is where Einstein's relativity enters with a second equally devastating constraint. The special theory tells us that as an object accelerates toward the speed of light, its relativistic mass, the resistance it offers to further acceleration, grows without bound. The closer you get to the speed of light, the more energy you must expend to accelerate by even a tiny additional fraction of that speed. At 90% of light speed, the mass increase is already significant. At 99%, it becomes enormous. At 99.9%, it becomes staggering. At 100%, it would require infinite energy, which is simply another way of saying it is physically impossible for anything with mass to reach that boundary. The universe has arranged its mathematics so that light speed is an asymptote, a line you can approach but never touch, and the approach itself demands exponentially escalating investment of energy. So let us be generous. Let us imagine a civilization, not necessarily human, that has developed propulsion technology so far beyond our own that they can accelerate a spacecraft to 99% of the speed of light. How much energy does that require? The answer depends on the mass of the vessel, and here is where the engineering reality collides with the physics in a way that leaves almost no room for optimism. To accelerate even a modest spacecraft, say one of 1,000 metric tons, to 99% of light speed using a perfect rocket, one that converts propellant into thrust with 100% efficiency, you would need a quantity of fuel whose mass dwarfs the spacecraft itself by an astronomical factor. The rocket equation, which governs how much propellant is needed for a given change in velocity, does not scale linearly. It grows exponentially. To reach high fractions of light speed, the ratio of fuel mass to final spacecraft mass becomes so large that even in principle, even with perfect antimatter annihilation engines producing the maximum energy per kilogram that physics allows, the numbers push into territory that is not merely impractical, but arguably unreachable at any scale of engineering. Antimatter propulsion is often invoked here as the technological savior. Antimatter, when it meets its matter counterpart, annihilates completely and converts 100% of its mass into energy via Einstein's relation connecting energy, mass, and the speed of light. No other reaction in physics extracts more energy per unit of mass. And yet, even antimatter annihilation, the theoretical ceiling of chemical and nuclear rocket propulsion, produces thrust that is still subject to the rocket equation. You still need to carry the antimatter with you. The antimatter itself has mass. Producing antimatter requires energy, staggering amounts of it. The most optimistic interstellar mission concepts based on antimatter, even those designed only to reach Alpha Centauri in human-relevant timescales, require quantities of antimatter that exceed our current global production capacity by many orders of magnitude. For a galactic crossing, the numbers don't merely become challenging. They become physically absurd. There is a separate category of proposed solutions that deserves serious engagement because it emerges not from engineering ambition, but from general relativity itself. Einstein's general theory showed us that space-time is not a rigid backdrop, but a dynamic, flexible geometry that can curve in response to the presence of mass and energy. This gave physicists the mathematical freedom to ask whether the fabric of space-time might, under certain conditions, be bent or folded in ways that would allow shortcuts. The most famous of these is the wormhole, technically known as an Einstein-Rosen bridge, a hypothetical structure that would connect two distant regions of space-time through a tunnel, a throat, so that you enter at one end and emerge effectively instantly at a point that is light years away in ordinary spatial terms. The physics does not flatly forbid these objects. The equations of general relativity permit solutions that contain them. But the physics attaches conditions that are, to put it plainly, staggering. To hold a wormhole open to keep its throat from pinching off in an instant, you would need something called exotic matter. Not exotic in the colloquial sense of unusual or rare. Exotic in a very precise technical sense, meaning matter with negative energy density, matter that in effect pushes outward against gravity rather than pulling inward with it. We have tantalizing hints that quantum field theory permits certain configurations of negative energy density in very restricted microscopic circumstances. The Casimir effect, which produces a small attractive force between two unchilled conducting plates placed extremely close together in a vacuum, is often cited in this context. But the quantities of exotic matter that would be needed to stabilize a traversable wormhole of useful size, one large enough to admit a spacecraft, are extraordinary, likely on the order of the mass-energy equivalent of a planet, configured in a way we have no physical mechanism to produce. We do not know whether exotic matter of the required type can even exist in the universe at macroscopic scales. And there are additional theoretical arguments suggesting that quantum effects would destabilize any traversable wormhole the moment a signal or an object attempted to pass through it. There is also the Alcubierre drive, a concept proposed in 1994 by physicist Miguel Alcubierre, which represents perhaps the most creative attempt to circumvent the light speed limit using general relativity. The idea is elegant in its conception. Rather than moving a spacecraft through space, you modify the space around it. You contract the space-time in front of the vessel and expand it behind, creating a bubble in which the ship sits stationary, while the bubble itself and everything inside it moves at any speed you choose, including faster than light. Locally, inside the bubble, no laws of physics are violated. The ship is not moving through space at faster than light speeds. The space around it is doing the moving. But the Alcubierre metric, the mathematical description of this space-time configuration, requires even more exotic matter than the wormhole. Quantities that, when estimated by physicists, turn out to be comparable to the total mass energy of the planet Jupiter, arranged in configurations that nature provides no mechanism for achieving. Later refinements of the concept reduced these requirements somewhat, but never to anything approaching a range that physical reality could accommodate. The Alcubierre drive remains a mathematical curiosity, a proof that the equations of general relativity have exotic solutions, not a blueprint for a technology. Let us add a third dimension to this problem, one that involves not energy or space-time geometry, but time. Even setting aside propulsion entirely, crossing the galaxy introduces a temporal obstacle of its own kind. At high fractions of light speed, special relativity produces a remarkable phenomenon called time dilation. Clocks aboard a fast-moving spacecraft run slower relative to clocks at rest. The effect is real. We measure it in particle accelerators every day in the extended lifetimes of muons generated in the upper atmosphere as they travel toward the ground. For a spacecraft traveling at 99% of light speed, time aboard runs at roughly 1/7 the rate it does for a stationary observer. At 99.9%, that ratio climbs to 1 to 22. This means that a crew could, in principle, experience a crossing of significant distances in a subjective time much shorter than the light travel time. A crossing of 100,000 light years at 99.99% of light speed might take the crew only a few centuries of their own biological time. But the word must be loaded with caution. First, achieving that speed demands the energy expenditure already described, which remains in the physically inaccessible range. Second, the civilization sending the ship would wait not centuries, but 100,000 years for any signal that the mission had concluded. The home civilization, any planet, any culture, any record of origin would have changed beyond recognition or ceased to exist entirely. The travelers would arrive in a galaxy that had moved on without them, around stars and planets born after their departure, in a universe that had advanced 100,000 years since anyone they knew had last drawn breath. Time dilation solves the subjective duration problem for the traveler at the cost of severing them from everything they knew in a way that cannot be reversed. The traveler comes home to a future so distant that home no longer exists. There is also the question of what space actually contains along the way. The interstellar medium is not empty. It is permeated by hydrogen atoms, dust grains, ionized gas, and at the densities encountered in the plane of the galactic disk, a spacecraft traveling at relativistic speeds would encounter this material not as a gentle mist, but as a ferocious bombardment of high-energy particles. At 90% of light speed, each hydrogen atom in the path of the ship strikes the hull with an energy comparable to a cosmic ray particle. The flux of such impacts at galactic crossing speeds would deliver a radiation dose to both crew and electronics that no known shielding material could adequately attenuate without adding so much mass that the propulsion requirements become still more impossible. The galaxy is, in a very real sense, lined with a radiation field that becomes lethal at the speeds that would make crossing it possible in biological timescales. What all of this converges on is a picture of the cosmos as a place of magnificent, terrible scale. The universe did not arrange itself for the convenience of biological organisms. It operates on timescales of billions of years, on distances of trillions upon trillions of kilometers, governed by laws that apply uniformly and without exception. Those laws do not carry any special provision for the ambitions of a species that has been technologically capable for a few centuries out of the 4.5 billion years its home planet has existed. The light speed limit is not a puzzle left for the sufficiently clever to crack. It is a geometric property of space-time embedded in the very structure of the universe at the deepest level of mathematical description we possess. The energy requirements imposed by the rocket equation are not an engineering challenge awaiting a breakthrough material. They are consequences of conservation laws that every experiment ever conducted has confirmed without exception. And yet this is not a counsel of despair. It is something far more interesting. It is an invitation to take the universe seriously on its own terms. The constraints that forbid galactic travel are the same constraints that give the cosmos its structure, that cause light to propagate at a fixed speed, that make mass curve space-time, that permit stars to burn for billions of years, and planets to coalesce from the debris of earlier generations. The same physics that confines any civilization to its corner of the galaxy is the physics that made the galaxy in the first place, that seeded it with carbon and oxygen and nitrogen through the violence of supernova, that generated the planetary conditions in which chemistry complex enough to ask these questions could eventually arise. We are creatures built by the same physical laws that prevent us from crossing the galaxy. Our curiosity about those limits is itself a product of the cosmos understanding its own structure through the medium of minds. The dream of sailing between the stars is not diminished by knowing why it is so profoundly difficult. If anything, it is clarified. We see more precisely what the universe is, what it permits, and what it does not. And in that clarity, there is a kind of wonder that no amount of technological optimism can manufacture. The wonder of a species that figured out, using nothing but mathematics and careful